Okay, everyone, we are back now with section 4.1.4, studying something called Fisher's linear discriminant. So another non-probabilistic but kind of interestingly motivated approach to for determining the weights for doing classification. So we're going to talk about the kind of the two-class case first, and then in a couple of sections we'll talk about the multi-class case. Okay, so one way to view a linear classification model is in terms of dimensionality reductions. That's already pretty cool, right? Like, I wouldn't have thought of that. Consider first the case of two classes, and suppose we take the d-dimensional input vector x, you guys can see, okay, and project it down to one dimension using just like that, okay? Now, if we place a threshold on y and classify y is greater than minus w naught as class C1 and otherwise class C2, then we obtain our standard linear classifier that we've already talked about. Now, in general, the projection onto one dimension leads to a considerable loss of information. Okay, yeah, you're throwing away lots. You're projecting, away lots of dimensions. And classes that are well separated in the original d-dimensional space may become strongly overlapping in one dimension. However, by adjusting the components of the weight vector w, we can select a projection that maximizes the class separation. And one thing I just thought of is, like, back in the day when all these methods were coming up, people were coming up with them, they had kind of low dimensional data, and they were okay with, I guess, doing some of this, throwing away some of this information. They just wanted to be able to get some kind of a handle on the problem. They didn't have like enormous computers. They had to come with these very kind of simple methods that kind of capture everything. Whereas kind of the contrast to now, where we have tons of data, we can use very complex methods to explain our data, but then maybe it's not so easy to understand kind of what's going on under the hood. But anyway, minor comment. Okay, so now by adjusting the components of the weight vector w, we can select a projection that maximizes the class separation. Okay, so I think that's kind of just to understand what he means. It's easy to just look at a picture. So this is another one of his great pictures. So the idea is you've got like two classes. There is one and there is two. And now you're going to choose, we're going to project them. So this is two-dimensional data. You're going to project it along one dimension. And the first one you might think of is the difference between the means. And if you do that, well, you'll see, hey, like these guys are really separable in the original space. But when I've projected, they're actually not separable. So the idea with the Fisher's linear discriminant is actually to find a direction in the space that kind of accounts for their tilt of the data, that makes sure that even in this low dimensional projection, they still remain separable. Okay, so again, like you have large data. Can we find a low dimensional projection that maintains that separability? Okay, so let's get back to it. To begin with, consider a two-class problem in which there are n1 points of class C1 and n2 points of class C2, and then we're going to define their component means that way. So notice that we're just looking over the points that are in each one class or the other class. The simplest measure of the separation of the classes when projected onto W is the separation of the projected class means. Okay, so that would be, that's probably what you would come up with first, right? So this suggests that we might choose W so as to maximize the projection of that difference onto our weight, where these are these are the class means. But this expression can be made arbitrarily large. Okay, so we have to make sure W has length 1, blah, blah, blah. But there's still a problem with this approach, right? Which is what we just saw. Two classes that are well separated in the original two-dimensional space, but have considerable overlap when projected onto the line joining their means. So that the mean idea is not exactly what we want to do. This difficulty arises from the strongly non-diagonal covariances of the class distributions. So now this is a key bit. The idea proposed by Fisher is to maximize a function that will give a large separation between the projected class means while also giving a small variance within each class. So it's going to, large separation between and small within each. So you want them to be tight. So you want to project so that, like, you're within classes, they're very tight, but between classes, they're far apart. And if you're going to go back to this example, you can see that, like, even within classes, they're just not very tight, right? The distributions are quite broad. Whereas here, they're a little bit tighter, and now they're well separated. And the two classes are well separated. So the question is, how do we do that? Okay, so that's good. Okay, so now the projection formula, which was just this, transforms a set of labeled data points into a labeled set in one-dimensional space as the output space. And so we can then just compute their within-class variances. So this is just like that. We can define the total within class variance. So let's just do that total. Total within class variance for the whole data set to be this. Fine. The Fisher criterion is defined to be the ratio of the, let's highlight this, the ratio of the between class variance to the within class variance. And it's given by this. So the ratio of the between class variance, that's going to be this top part on top of the total variance. So sorry, the within class variance, which is total within class variance. Okay. Okay, and then he says, look, we can make the dependence on W explicit. So we're just going to plug in all of these different formulas we had for all of these terms, and we can express it as, we can express this, you know, between class versus within class variance as this particular expression. And now we're going to define our between class covariance. So that's kind of the outer product of the difference between the means. And the, oops, let me zoom in a bit more. Yeah, much better. Okay. And SW is a total within class covariance matrix, which is you're just summing the data points in each class relative to their local class means. Notice there's no like weighting of them, you know, by 1 over n1. It's just, you're just summing that up. And then if you just differentiate this with respect to W, you end up getting this relationship here, which is, you can think of it another way, you know, it's kind of, for example, a generalized eigenvalue problem. Yeah, you know, with the normal eigenvalue problem, you have like ax is equal to lambda x. Here we have like ax is equal to lambda b of x. And so you can write this as, it's an eigenvalue problem for w beta 1 a over x. So just kind of a bit of something to know about. Okay. So we're kind of looking for these eigenvectors, which are going to extremize this kind of ratio. So you can, kind of goes back to what we're measuring here, ratio, either being very large for one of these and small for the other, or vice versa. Now we see that SBW is always in the direction of the difference in the means. Therefore, and because we don't care about the magnitude of W, we're always going to normalize it to 1. These constant terms here are going to disappear. And, oops, let me just erase all this stuff. And multiplying both sides of 4.29 by SW minus 1, we then obtain this expression. Okay, and so, so the cool thing about the expression is that, again, so we've got our mean, the difference in the means showing up, but now it's being kind of adjusted by the within class covariance. I tried to get kind of some intuition for this. So if we actually kind of look at it, so if we do kind of an eigendecomposition on SW, we'll get, well, W is proportional to, here is, and these are going to do U transpose M2 minus M1, right? So then this goes to saying that, well, you know, if we go UTW is equal to 1 over L UT M2 minus M1. So in these kind of rotated coordinates, it's going to equal to 1 over L of the rotated coordinates between the means. So for example, you know, if you've got your, you know, your covariance is kind of going like this in the same direction, you first kind of rotate the data. Maybe you get something like this, and then those rotated coordinates, you've got this difference in the means, and now you're just going to scale that difference in the means by 1 over L. I don't have like a great intuition for why that's the case. So if I do come up with something, I'll let you guys know. I tried to think about it in the case of when, you know, let's assume your data is already flat, right? So your U's are already already the, you know, the normal axes, and so all you end up doing is kind of scaling this difference between the means, and so that would make your W something like that, which kind of makes sense. So if you're projecting this data along that particular direction, yeah, you do kind of separate it. But I don't have a better intuition than that for why the 1 over L would show up. I think all I can say at this point is that, yeah, so the difference, the means is there, but you have to do some accounting for the covariance of the two classes. And he said, look, note that if the within class covariance is isotropic, so SW is proportional to the unit matrix, then W, so if this is the identity, then proportional, then W is proportional to the class mean. So if you've got, two circles like that, then indeed you should separate them by the mean. Okay, so the result of, let's erase all of this. The result is known as Fisher's linear discriminant, although strictly it's not a discriminant, just a specific choice of direction of projection for the data. Yep, technically that's the case. But we can do it to construct a discriminant by choosing a threshold, why not, so that we can classify a new point as belonging to C1 if the projection is greater than y naught and C2 otherwise. And then the idea is like, well, how do we go about doing that? Well, we can model the two classes using Gaussians, using maximum likelihood to get the parameters. And then we've got methods that we learned earlier in earlier sections on how to then pick a threshold between those. So that's kind of how you can do it. And finally, the Gaussian idea is not too bad because you're going to be summing up a bunch of random variables, and often those such sums, if you have enough of them, are kind of well approximated by Gaussian. Okay, so I think that's all I wanted to say about this section. I think it's, again, a very cool idea of thinking about classification of dimensionality reduction, and then being able to do this kind of within class, between class, almost like analysis of variance idea. I'm trying to maximize that, and miraculously, you do get a closed form answer for all of this, which is pretty cool. I want to have a bit more intuition about this. I don't right now, but if some of you guys do, please let me know in the comments. But yeah. Good. So I think the key picture you want to keep in mind is this one. I think that essentially explains what's happening here, right? Like the class means not always the best. If the data has funky covariance, you want to account for that, and that's what the Fisher linear discriminant does. Okay, so I think that's all for this section, and I think next time we're going to be talking about the connection between least squares and the Fisher discriminant, and showing that actually the Fisher discriminant is a special case of least squares for a particular for a particular set of target vectors. Cool. Well, I hope you enjoyed this section, and I hope to see you next time. Bye.